right, so we can go ahead and get started. So my name is Erin D, and this is Wyzant's Getting Ready for High School Chemistry. This is a basic introduction to chemistry. It should help you to get ahead or start with a head start for your high school class. We're discussing definition and classification of matter, which is what all of chemistry is about. The language of chemistry, so it doesn't look so foreign to you. And then physical and chemical properties and changes. So if you have questions, feel free to drop them in the Q&A box, and I can look at them as we go through, or I'll definitely get to them at the end. And we can go ahead and get started. So first of all, let's start with a definition of chemistry. So chemistry is essentially the study of the substances around you. Everything around you consists of matter, what we call matter. So chemistry is basically all about matter and how matter changes, or how these substances change. I always tell my students that everything is related to chemistry somehow, but not everything is considered matter. So if you think about it, we can go through pretty much anything you can think of in your mind. I can relate it to chemistry somehow. In fact, I told every kid in my class at one point, I'll give you an A if you can find me something that's not related to chemistry. However, that doesn't mean that everything is considered matter. So we're going to go through the actual definition of matter and how matter changes. So what is matter? Two things matter has to have. Matter has substance, which is considered mass, and it takes up space, which is considered volume. So substance is like actually atoms, like things in a substance. So how many atoms are in that substance? So that's essentially what mass is. And then the fact that it takes up space. So matter must have mass and volume to be considered matter. Mass is measured with a scale, which I put over here. So mass is essentially the definition of mass, we say, is the amount of stuff in an object or thing. And we measure this using a scale. So a scale measures mass. You've probably heard of a scale before to measure pounds. Pounds is a little bit different than mass. It has more to do with gravity, versus mass is just a measure of how much stuff is in an object. So in chemistry, mass is typically reported in grams, which is what we have on the scale here. So we can see the unit is grams. And then volume is the amount of space taken up by an object or thing. So we can measure volume. You've probably done this in math before, where you've said, okay, volume is length times width times height. And we can do this with any regular object. So any cube or rectangle or square object that has length and width and height, and it's a regular object, we can easily measure this with usually a ruler. But then when we get into liquids, that's a little bit more difficult to measure volume this way. So we do this with a beaker or a graduated cylinder. And so you can see the tick marks here. We typically measure volume in chemistry in milliliters. And then for irregular objects like a rock or a stone, or sometimes a marble of some sort, something that's not easily measured, we can measure this using water displacement to measure volume. So we can look at the original volume, which looks like it's, I can't really read this, about 150 milliliters. And then when we drop the stone in, now it's about 175. So we can just take the difference. So 175 minus 150 is roughly 25 milliliters in volume for this stone. So this is a quick and easy way that we can measure volume via water displacement. And like I said before, volume is typically measured or reported in milliliters, or if we're doing it the length times width times height method, then we report this in centimeters cubed. Because we're taking centimeters times centimeters times centimeters. So volume and mass. So both of these things constitute matter. So if there's something that does not have both volume and mass, then we can't consider it matter. Most things that we think of that we can look at and hold in our hands are all considered matter. But there are things that we don't consider matter. So let's go through this list really quick and see if we can distinguish what's matter and what's not. So what is considered matter? Everything, again, can be related to chemistry, but not everything is considered matter. So rain, rain is technically water and other salts that fall. So can we take the mass of rain? Can we take the volume of rain? Of course, so we consider this to be matter. Cars, those are obviously visible. You can touch and feel cars. These are also considered matter. Happiness. So some things, I always say everything is related to chemistry, and I can say happiness and feelings are related to chemistry because they relate to chemicals in your brain, but the feeling itself, we do not consider to be matter. So feelings, as well as energy, so sound is a form of energy, we do not consider this to be matter. It doesn't have mass or take up volume. Now, I still say sound is related to chemistry because chemistry does involve energy, but not specifically matter. Wind is the movement of air particles. So we consider air to be matter, but not necessarily the movement of matter. So we would consider wind to not be matter. And then air, like I said, air is considered matter. Air is made up of several different gases, one of them being oxygen. So we consider this to be matter. And then light is another form of energy. So we do not consider light to be matter. And then finally, we have atoms, which we know, we've heard of atoms before, commonly associated in chemistry or with chemistry. So we consider atoms to be matter. Even though they're small, they do have mass and take up space. So we consider them to be matter. And when they're combined together in large quantities, we get actual things that we can see with our eyes. Okay, so first, before I dive into like more of matter and sorting of matter, because that's kind of the first thing that you guys are going to see in your chemistry classes is classification of matter. I wanted to kind of take a tangent and talk about the chemistry or the language of chemistry, because this is important. I think so many students get lost when they start chemistry because they are so bombarded with this foreign language that, you know, they have no idea what it's talking about. So I wanted to go through and just outline the chemistry language. So in chemistry, we talk in terms of elements, which are specific types of atoms. We've named all of the 118 elements on the periodic table. And these are the basic building blocks of everything that we know to be matter. So everything is made of one of these elements or multiples of these elements. So when we abbreviate these elements, we abbreviate them in the form of chemical symbols. So this is either one or two letters. And the first letter always starts with a capital letter. So this is how you know you're talking about an element and maybe only one element. So if there's two letters within the abbreviation, for instance, FE, the second letter will be lowercase. So this is concerning only one element. Now, if you have two letters that are both capital, then you're considering or you're talking about two different elements. So each element will only have one uppercase letter in the abbreviation. So sometimes the symbol is a direct abbreviation of the name, and then sometimes it's not. Sometimes it's totally different. And so this isn't just to confuse you, even though it is confusing. Some of these symbols are an abbreviation of an older term, usually the Latin word for the name. So carbon, for example, we abbreviate with just a single C. So this is indicating carbon. Helium is HE. So these two are obvious because they abbreviate the name that we know of them. But then we have gold, which is on the periodic table as AU. So AU is an abbreviation of the Latin term for gold, which was aurum. And then iron is the same scenario where the name of the element is iron, but the abbreviation is Fe. So this is an abbreviation of ferrum, which is the Latin term for iron. Another example of this is silver. So silver's abbreviation is Ag, and this is the abbreviation for argentum, which is the Latin term for silver. Okay, so further chemistry language. So we have single elements and then we have compounds. So this is probably what you've seen more of when we talk about chemistry. So it's important to note, you don't have to name these yet, but you'll learn. But just when you look at a compound or when you look at something like this, so you see two different capital letters. So that right there tells you there's two separate elements within this compound. But the compound basically tells us specific ratios of each of how those elements are combining. So this compound H2O tells us that there's two H's and there's one O. So the subscripts that follow each capital letter are pertaining to the amount of that element. So the H's and O's combine in a 2-to-1 ratio, and this tells us the specific ratio of this compound. Another example is NaCl. So again, this is Na, which is abbreviation of sodium, and then Cl is chlorine. So two different elements in this compound, and these are in a 1-to-1 ratio because we only have one Na and one Cl. So when you see a compound, this just means two different elements bonded together, chemically combined together, or maybe more than two elements. And it gives you the basic ratio of that compound. Okay, so now that we've gone through chemistry language, we can talk about the physical forms of matter. So we know what matter is, we know how to measure matter, but how do we see matter in nature? So this is when we get into physical forms of matter. So solid, for instance, there's three physical forms, and then there's three physical phases of matter, and then there's another form of matter that we talk about. So the first one, solid, and we abbreviate this with an S following the compound. So this is indicating that this is water in a solid form. And then a description of this would just be ice. So this is solid. We can think of solids. When you get further into chemistry, you'll learn the actual definitions of solids and then liquids and gases. So liquid is another physical form or phase of matter. We abbreviate this with an L following the compound. Example of this is just water, liquid water. And then we have gases. So this is the third phase of matter. Abbreviate this with a G after the compound. And an example of this is steam. So water vapor or steam. So all of these are different physical forms of water. So they come in different forms and they look different to our eyes, but they're the same actual chemical. In the end, they're just in different physical forms. And then we have this other form called aqueous, which is, we classify this as a form. It's not necessarily a phase. It technically means whatever this compound is, which is in this case is NaCl, so this is table salt. When we say aqueous, this just means this is salt dissolved in water. So anything with an aqueous following this compound means that it's technically dissolved in water. So the majority of that physical form will look like water, and it's just dissolved in water. So back to matter. Matter overview. So I'm going to go through the classification of matter. So this is the basic classification. So we have atoms, which are the basic forms of matter, or simplest particle retaining properties. So an atom and an element, we use these terms synonymously in chemistry. So we typically say element. Atom is kind of like the generic element. Element is a specific atom. An element just means one or more of the same type of atom. So typically we're talking about one element when we refer to element, but if it's the same type of element, we still call it an element. So for instance, H2 and O2, this is like hydrogen gas, oxygen gas, these are considered elements. And then we have compounds, which are different elements bonded together to make a compound. So how do we know it's a compound and not an element? They have to be two separate elements bonded together. So how do we know they're bonded together? Basically, they're written as one formula. And then we have mixtures, which are different compounds that are physically mixed together. So mixtures are the majority of what we encounter in everyday life. We don't really encounter pure water ever. Even when we think we're drinking water, we're drinking a mixture of water and some salts or sediments dissolved in water. and air, for instance, we're never breathing pure oxygen. We're always breathing a mixture of oxygen and other gases. So the majority of time in real life, we're dealing with mixtures and not these pure substances, which are like elements and compounds. Okay, so this matter classification chart, this is typically introduced in the first couple of weeks of regular general chem in high school. So it's good to know. It's helpful to be able to classify matter, look at something and say, is this a compound, or is this a mixture, is this a pure substance? So matter can be classified into two main substances. So I say either a pure substance or a mixture. So the main differences between these two is that mixtures can be physically separated. So physically means they're not going through a chemical change, which we'll discuss in a second. So examples of a physical separation are things like filtration or distillation, where you're boiling water out of a salt, something like that. That's like what they do on Survivor, where they like leave a bucket of water out in the sun with a tarp, and then the water like boils off. So this isn't actually changing the substance. You're just physically separating two entities. Like you're usually separating the water from the salt, or you're separating, like if you wanted to filter out water from sand, then you could use a small filter. So a mixture can be physically separated, whereas a pure substance must be chemically separated, or cannot be physically separated. And there's only certain pure substances that can be chemically separated. So these are the two main categories of matter. So we'll look at mixture first, because like I said, this is what we deal with mostly in everyday life. So this will seem more familiar to you. So mixtures can be separated into two different categories, either heterogeneous mixtures or homogeneous mixtures. So what the difference is hetero means different. So a heterogeneous mixture means the concentrations throughout this substance are different in different areas if you were to like look at the concentration. So for instance, salad dressing, which is what I have here pictured here. So if we leave salad dressing to sit for a little bit, we'll see that there's a layer of usually more solid particles that will drop to the bottom of the salad dressing. And so if you were to grab a sample of this salad dressing, either at the top of the bottle or at the bottom of the bottle, you would see that the concentrations are different throughout the bottle. And so this would constitute a heterogeneous mixture. Other examples, ocean water. So again, if you were to grab like just a bucket of ocean water, well, ocean water is typically some sand and some salt and some water and maybe some creatures and some dirt and whatever else we find in there. So, and this is not mixed evenly throughout. So another example of a heterogeneous mixture. And then we have homogeneous mixtures, which are more uniform throughout. So these are things like solutions that are evenly mixed throughout. So if you were to grab a sample of one of these, like for instance, lemonade, gasoline, you would get the same lemonade throughout the whole mixture of whatever your pitcher that you're pouring out of. And then of course gasoline as well. We try to make sure gasoline is homogenized to make sure that we're getting the same concentration throughout the sample of gasoline. And then steel is another example of a homogeneous mixture. So steel is technically considered an alloy. And alloys are basically mixtures of metals. So steel is something that's not on the periodic table. It's an alloy, which means it's two metals or two elements mixed together. So these are also considered homogeneous mixtures. And then we have pure substances over on this side. So compounds as well as elements. So compounds can be separated. So something like salt, which we know is NaCl now. So this can be separated into its elements Na and Cl, but not easily. This would take a chemical reaction in order for this to happen. Actually, salt dissolves in water, so really this would dissolve in water, but other things like sugar, baking soda, water, so these, if you wanted to to actually break the bonds of H and O in water, then this would take a chemical reaction in order for this to take place. And then we have elements. So elements cannot be separated unless we're doing something atomically. So something like hydrogen, oxygen, silver, or platinum. So these are elements. They are the basic building blocks of matter, so they cannot be separated. And I included this last because elements are typically, we don't encounter elements like pure elemental forms as much as we encounter mixtures of different elements in everyday life. So this category seems the most familiar to you versus this category, which is like pure elements. Okay, so between the differences between pure substances and mixtures is that, again, mixtures you can separate physically, pure substances you can't. To go from a mixture to a pure substance, this is considered a physical change. And then to go from a compound to an element, so breaking the compound down into its elements, this is considered a chemical change. So we'll talk a little bit more in depth about physical and chemical changes in a second. Okay, so just as a checkpoint, let's go through these to make sure we kind of understand the differences. So we have several different examples here. So hydrogen gas, we would say, is a pure substance and considered an element. Air, so we talked about air just a little bit earlier. So air, remember, this is a common misconception. A lot of students think air is just oxygen, but it's not. It's a mixture of multiple gases, and so we would consider this a mixture, but a homogeneous mixture. So it's pretty evenly mixed throughout. Table salt is considered a pure substance. So remember, again, if anything you've learned from this, you now know that table salt is NaCl. Gatorade is a mixture, and we consider this a homogeneous mixture. If you look at Gatorade, it looks like a liquid. You don't actually see the particles and all the sugars and the salts dissolved in Gatorade. It would just look like a liquid. And that's mostly what homogeneous mixtures look like. They look like they're liquids or pure substances, but they're actually multiple things dissolved. Then we have brass is another example of an alloy. So brass is a mixture of copper and zinc. So because of this, we consider this a mixture because it's multiple compounds and they are mixed together. They're not like necessarily chemically bonded together. And this is a homogeneous mixture because it's evenly mixed throughout. Copper, on the other hand, is an element on the periodic table. So we consider this a pure substance and we call it an element. And then pizza and soil are both heterogeneous mixtures, not evenly mixed throughout. And we can visibly see the differences. So we call them heterogeneous mixtures. Okay, so other properties of matter. So these are two separate properties of matter, physical and chemical properties of matter. So physical properties can be observed without changing the substance into a new substance. So something like color, so like red, green, and blue, these are physical properties of matter. I can easily observe this and I don't have to either change or destroy the substance in the process. Other examples of physical properties: boiling point, mass, volume. So all of these properties are easily observed. You can observe these without changing the substance. So you might not realize what that means. So I'll go through chemical properties just so you can compare the two. So chemical properties are properties that you can only observe when you change that substance into a new substance or destroy the substance. So something that I always like to talk about is flammability. How do you know a substance is flammable without lighting it on fire? You don't, so you light it on fire. So in order to observe that property, you're essentially lighting the substance on fire, which means you're destroying it or you're changing it in some chemical manner. So this would be considered a chemical property. Another chemical property is corrosiveness. So how does it corrode, or how does it rust, or how does it oxidize? These are things that happen. These are chemical reactions, and the only way we know if it's corrosive or if it's rust proof is if we actually make it rust, which means we're going through a chemical change. And then again, reactivity. So how do we know if something's reactive? Well, we have to react it with something else, which means it's going through a chemical change. So these are chemical properties. We can only observe them by changing these substances into new substances or destroying them. So physical properties as a whole are a little bit easier to observe. And then we have, so density is kind of another tangent that I want to go through, because this is a term that relates both mass and volume and is also considered a property of matter. So density is the mass of a substance per unit volume, or how close together all the stuff is in an object. So if you look at these two boxes, this object would be considered more dense because these objects are closer to themselves. So you can fit more spheres in this container versus this container because the density, like the space between the objects, is smaller here. So this one would be considered more dense. So why does chemistry concern itself with density? Because it relates the two things that are most important in chemistry, which is mass and volume. So density is mass divided by volume. I always like to use this density triangle. Some students, if you struggle with algebra or you are not sure how to rearrange this equation to solve for other variables, you can always use this triangle and just cover up the variable that you're looking to solve for. So if you cover up density, then the equation is mass over volume. Or if you cover up mass, which I already covered up density, then mass would equal density times volume. So you can always use this density triangle to solve for other variables in this equation. Okay, so why do we care about density? Because it's another property of matter. So is it a chemical property or is it a physical property? Can we measure this without destroying the substance? And the answer is yes. We can measure mass and we can measure volume without actually destroying the substance. So this would be considered a physical property. And the reason why is because it's easily measured. We can measure this without destroying the substance. Why does density matter? Because we can use it to identify matter. So this was a way that they used, especially to identify gold a while ago, before they could test like reactivity easily, is they use density. So gold is extremely dense compared to like brass, which is another gold-looking substance, but not as dense as gold. So density, again, remember, is mass over volume. How do we measure density? We have to measure the volume and the mass of everything, and then just take the density equation and divide mass divided by volume. So this tells us that the sides for this cube are 2.1 centimeters each. So we just have to take 2.1 and multiply it by, or cube it, 2.1, 2.1, which equals 9.26. And then the mass is already given to us. We would assume that they measured this mass of the cube is 178.5. And then we just take 178.5 divided by 9.26, which gives us 19.3. So what does this tell us? Well, we can look at a graph of known densities of metals and compare them. So every metal has a known density. It doesn't change. It's like an inherent property of that chemical. So brass, which is commonly confused with gold because it looks the same from the outside, but it definitely is not the same density. So brass sometimes would be given to people and they were told, you know, it's gold, but we could measure the density easily and see that this substance is in fact gold and not brass. But usually it happened the other way around. It was given to them saying it was gold, but it was actually brass. So again, like, we know these terms. These are known terms in chemistry of just densities of common metals. And so we can use this, whatever we find for the density, to compare it to known densities that we can look up to see what the metal is. So which block could be made of this block could be made of which metal? It would be gold. Okay, so going back to, and again, density is a physical property. Going back to matter, physical and chemical changes, physical and chemical properties, the last thing we'll talk about is the changes of matter. So I said chemistry is the study of matter and also the changes of matter. So matter goes through two separate changes. We have physical changes, which do not change the composition of a substance, and then chemical changes. So physical changes, examples of This are changes in temperature, changes in state, so going from a solid to a liquid to a gas, or back from a gas to a liquid to a solid. This would be an example of a physical change because we're not actually changing the substance. It's still water the whole time. And changes in volume. So you can shrink the volume of water, like you can pour volume out. This is not changing the substance itself. It's just changing the physical characteristics of that substance. And then we have chemical changes. So these are changes that result in new substances. Combustion, oxidation, decomposition. So these are types of reactions, which you probably don't know these terms yet, and that's okay. We're going to go through just one quick example slide to see what these actually mean, or how we can put this into an example. So physical or chemical properties in this column and physical or chemical changes. So let's do this column first. Physical or chemical properties. So remember, physical property is easy to observe. You don't have to change the substance in order to observe that property. So the color of an element or the color of a sample of matter is a physical property. I can easily observe this and I don't have to change anything. Reactivity. Well, the only way to observe this property is by making this element or this substance react with something else, which will change it chemically. So this is a chemical property. Toxicity is also a chemical property because the only way to observe this is typically by making it react with something else. Toxicity is like how harmful it is to other organisms. So typically, if it is toxic, that means it's reacting and it's causing a chemical change in something else. So this is a chemical property. Length is something easily measured. You don't have to destroy or change the substance. So we would say this is a physical property. Density would also be physical. Flammability would be chemical because this is something that you would have to light something on fire in order to observe it. And then smell and temperature are both easily observed and physical properties. And then this column over here is physical or chemical changes. So remember, physical change is something that does not involve changing the actual substance of that sample of matter. So boiling water would be an example of a physical change, and cutting the grass. So cutting the grass, you can't really, sometimes I explain physical and chemical changes as physical is easily reversible, but that's kind of a misconception because even chemical changes can be reversed technically, but cutting the grass is not easily reversible, so it's not a good example, but this is still a physical property because you're not actually changing the grass. It's still grass, it's just in two pieces now. Dissolving sugar in water, so this does not change the sugar or the water. The sugar is still the same chemical, it's just not with other sugar molecules. So we would say that this is physical also. Baking cookies is a really example of a chemical change. It's difficult to go back to raw cookie dough when you bake, but also this is whenever you add heat and something is changing like colors, this is typically a chemical change because you're actually changing the matter. It's changing into a different substance. Chemical bonds are breaking. Burning wood, same thing. This is a chemical change. Anything that involves like flaming something, burning something, wood is turning into a totally different substance, ash, and then other stuff. So this is a chemical change. Banana ripening is a chemical change. Again, this involves a color change, also a smell change, and this is typically a chemical reaction. Silver tarnishing is another example of a chemical change because this is the reaction of silver with oxygen. And then paper shredding, very similar to cutting the grass. Still paper in the end, it's just in different pieces. So this would be an example of a physical change. Okay, whew, that was a lot of chemistry. So we went through the definition of chemistry and the definition of matter, classification of matter, and how matter changes through physical and chemical changes. So I will go ahead and open up the Q&A box to see if anybody has any questions, or type in your questions if you have any questions. It doesn't look like anyone has any questions yet or now. So I hope that this was helpful, and that you will go to class a little bit more prepared and have a little bit more of an understanding of chemistry, and not be so bombarded by all of the difficult terms. Oh, you're welcome. So, and I believe next week I'll be doing this again. And we'll talk about actual numbers, which are difficult, like numbers calculating with scientific notation, everything else. So thank you guys for tuning in, and hopefully it was helpful. And Wyzant will email you a recording of this class, because I know I went fast and it was covering a lot of information, so I find that it's helpful sometimes to go back and pause, especially look at the diagrams. So have a good evening, and I will hopefully see you guys next week.